Everything in the universe that you can see, every star, every planet, every galaxy, makes up about 5% of what's actually out there. The other 27% is something we can't see, can't touch, and have never directly detected, but we know it's there. Today I'm breaking down every major piece of evidence for dark matter and what it might actually be, starting with the observation that broke physics, die galaxy rotation curves. Here's something that should make intuitive sense. The farther a planet is from the sun, the slower it orbits. Mercury whips around at 47 kilometers per second. Neptune crawls at about 5.4. That's just how gravity works. More distance means less gravitational pull, which means slower orbital speed. Simple. So, when astronomers started measuring how fast stars orbit the centers of their galaxies, they expected the exact same thing. Yet stars near the core should move fast, stars at the edges should move slow. Turns out, no. In the late 1970s and early 1980s, astronomer Vera Rubin and collaborator Kent Ford published a series of papers charting the rotation curves of spiral galaxies. Every single one showed the same bizarre result. Stars at the outer edges were orbiting just as fast as stars near the center. The rotation curves were flat, not declining, not tapering off. Flat. And radio telescopes measuring the 21-centimeter emission line of neutral hydrogen confirmed the same pattern in galaxy after galaxy, way beyond where any visible matter exists. Which is, not ideal for our existing models. Here's where it gets complicated. For those flat rotation curves to work under the laws of gravity, there has to be a massive invisible halo of something surrounding each galaxy, containing far more mass than all the stars, gas, and dust combined. Rubin herself put it plainly. The conclusion is inescapable that non-luminous matter exists beyond the optical galaxy. And this isn't some quirk of a few weird galaxies. The pattern holds universally, from nearby spirals to distant dwarf galaxies. Every galaxy we've measured is spinning too fast for the matter we can see to hold it together. Period. But if spinning galaxies weren't convincing enough, wait until you see what happens when light itself starts bending around invisible mass. Gravitational lensing. Here's where dark matter stops being an inference and starts being something you can literally see. Well, sort of. You can see what it does to light, which is almost cooler. Einstein's general relativity predicted that massive objects warp spacetime itself, bending light around them like a cosmic magnifying glass. So when a galaxy cluster sits between us and some distant object, it deflects the background light, producing distorted, magnified, or multiply-imaged versions of whatever's behind it. Basically, the universe has its own built-in lens system, and nobody asked for it. Strong lensing is the dramatic version. You get multiple distinct images of the same background object appearing in different positions around the foreground cluster, and when the alignment is just right, you get Einstein rings, perfect circles of warped light wrapping around the lensing mass. It looks like something a sci-fi artist would get fired for designing because it's too on the nose. Then there's weak lensing, which is way more subtle. Instead of producing obvious visual distortions, it causes tiny systematic stretches in the shapes of thousands of background galaxies. Individually, you'd never notice. But statistically, across enormous datasets, those distortions reveal exactly where mass concentrates. It's like reading fingerprints on a window by shining light through it at the right angle. Here's the thing. When astronomers map the mass causing all this lensing, it consistently does not match where the visible matter sits. Most of the lensing mass in galaxy clusters is completely invisible. The light-bending cheat code doesn't care whether mass glows or not. It just measures mass, period. And the mass is overwhelmingly dark. AI-assisted analysis has identified hundreds of new gravitational lens candidates in survey data, significantly expanding the known count and giving astronomers an entirely new set of markers for mapping dark matter distribution across the cosmos. And this method extends all the way to the edge of the observable universe. Distortions in the cosmic microwave background, caused by large-scale matter structures along the line of sight, provide independent confirmation that dark matter exists at cosmological scales. That's mass bending the oldest light in existence. But if gravitational lensing lets us see dark matter's fingerprints on light, the cosmic microwave background lets us hear its voice from the beginning of time. The cosmic microwave background. This is the universe's baby photo. And dark matter's fingerprints are all over it. The cosmic microwave background is relic radiation from when the universe was only 380,000 years old. No stars existed yet, no galaxies, nothing but a screaming hot plasma slowly cooling down after the Big Bang. When that plasma finally cooled enough for light to escape, it left behind a faint glow that still fills every square inch of the sky today. Here's the thing, that glow isn't perfectly uniform. There are tiny temperature variations across it, fluctuations so small they rarely exceed 1 part in 100,000. Sounds like nothing. But those microscopic differences encode the entire composition of the universe like a cosmic fingerprint. When scientists measure the CMB's temperature power spectrum, they find acoustic peaks, standing waves frozen in time, created by gravity pulling matter together while radiation pressure shoved it back apart. The positions and heights of those peaks depend on exactly how much baryonic matter, dark matter and radiation existed in the early universe. Change any ingredient even slightly, and the peaks shift. The Planck satellite measured these peaks with absurd precision. Dark matter density, 0.120 plus or minus 0.001. These are some of the most exact measurements in all of science, and they paint a very specific picture. Cold dark matter makes up roughly 27% of the universe's total energy density. Dark energy accounts for about 68%. Ordinary matter, everything you've ever seen or touched, is 5%. You, me, every star, every planet, every grain of sand on every beach, 5%. But here's where it gets really convincing. The ACT and SPT telescopes, completely separate instruments using independent measurements, ran the same analysis and got consistent answers. Different telescopes, different teams, same conclusions. That's not a coincidence, that's confirmation. And baryon acoustic oscillations in the large-scale galaxy distribution extend the CMB's testimony across billions of years, showing how those initial fluctuations evolved into the structures we see today. Every method, every instrument, every era of cosmic history points to the same number. Dark matter isn't a measurement artifact, it's a fundamental ingredient of the universe. But if the CMB is dark matter's fingerprint, the next piece of evidence is its mugshot. Because when two galaxy clusters slammed into each other at millions of miles per hour, dark matter did something that ordinary matter physically could not. The bullet cluster. This is the one. If dark matter evidence were a courtroom, the bullet cluster would be the security camera footage. Located about 3.7 billion light years away, the bullet cluster is the aftermath of one of the most energetic collisions between galaxy clusters we've ever observed. A smaller bullet cluster slammed straight through a larger cluster at roughly 4,500 kilometers per second. That's fast enough to cross the entire United States in about 1 second, which is, not ideal if you're standing in the way. Here's why this matters. When the two clusters collided, the hot gas from each one, the ordinary matter we can actually see, slammed into each other and slowed down dramatically. Electromagnetic interactions turned it into a cosmic traffic jam. The Chandra X-ray Observatory picked this up beautifully, detecting gas heated to around 100 million Kelvin. In composite images, that gas shows up pink. It's stuck in the middle where the collision happened. Makes sense. But the mass didn't stay with the gas. Gravitational lensing analysis, shown in blue on those same composite images, reveals where the actual mass is concentrated, and it passed right through the collision like nothing happened. The dark matter clumps from both clusters kept moving, separating cleanly from the hot gas and ending up ahead of it on either side. The ordinary matter got stuck. The dark matter didn't even flinch. If visible matter were the dominant mass component, this configuration is physically impossible. The gravitational center should be wherever the gas is. It's not. The mass is somewhere else entirely. That's dark matter on camera, and it gets better. The James Webb Space Telescope recently delivered one of the highest resolution mass reconstructions of this cluster ever produced, combining strong lensing from dozens of multiply image systems with deep, weak lensing data. The main cluster turned out to contain multiple subclumps, with a possible mass trail extending from the subcluster toward the main cluster. The merger history is way more complex than anyone initially assumed. Now, here's a wrinkle nobody expected. Standard cold dark matter simulations struggle to reproduce the observed infall velocity. The shock velocity sits around 4,700 kilometers per second, which pushes the upper limits of what lambda CDM cosmology can comfortably generate. So, the bullet cluster proves dark matter exists and then immediately creates a new headache about how fast it was moving. Classic, but velocity problems don't stop at individual collisions. They show up across entire galaxy clusters too. Galaxy cluster, velocity. Here's the thing, everything we've talked about so far was discovered relatively recently, but the first person to actually find evidence of dark matter did it in 1933, and nobody believed him for 40 years. Fritz Zwicky was a Bulgarian-born Swiss astronomer working at Caltech, and he was studying the Coma cluster, one of the largest galaxy clusters we know of. Over 1,000 galaxies packed into a region spanning roughly 20 million light-years across, all enveloped in X-ray emitting gas heated to about 100 million Kelvin, which is, toasty. Zwicky used spectroscopy to measure how fast individual galaxies were moving within the cluster. Then he applied the virial theorem, which is basically a physics relationship connecting how fast things move in a system to how much gravity is needed to keep them from flying apart. Think of it like spinning a ball on a string. The faster you spin it, the stronger the string needs to be. The galaxies in the Coma cluster were moving at velocity dispersions exceeding 1,000 kilometers per second. That's absurdly fast. Zwicky did the math, and the result was genuinely shocking. The mass required to hold those galaxies together was roughly 400 times greater than what visible matter could account for. Not double, not triple, but 400. So Zwicky proposed the existence of Dunkelmaterie, dark matter, in 1933, and the scientific community said no thanks. The guy was right about one of the most important discoveries in astrophysics, and everybody just ignored him until the 1970s. Cool, add that to the list. Part of the problem was Zwicky himself. He was brilliant but notoriously abrasive, which didn't exactly help his case when asking people to believe in invisible mass. But here's what makes his work even more impressive. Contemporary measurements haven't just confirmed his findings, they've expanded on them. Stellar velocity dispersion turns out to be a direct, unbiased tracer of dark matter halo velocity dispersion. That correlation holds without evolution all the way out to redshift z less than 0.7, meaning it reflects fundamental physics established early in galaxy formation. Zwicky didn't just stumble onto something weird, he found a universal relationship between visible galaxies and the invisible halos surrounding them. So we've now seen dark matter separate from regular matter in collisions, bend light across the cosmos, flatten rotation curves, and hold galaxy clusters together against impossible speeds. The evidence is overwhelming, but what actually is it? The leading candidate has a name that sounds like it belongs in a children's cartoon: WIMPs. So we've established that dark matter is real, it's everywhere, and it outweighs everything you've ever seen by a factor of 5 to 1. The obvious next question is, what is it? And for the last few decades, the single most popular answer has been WIMPs, the weakly interacting massive particles. More money, more experiments, and more published papers have been thrown at this one candidate than every other option combined. Here's the pitch. WIMPs are hypothetical particles that interact only through gravity and the weak nuclear force, the same force responsible for radioactive beta decay. They'd have real significant mass, but they'd be completely invisible to every telescope ever built because they don't interact with light at all. Zero electromagnetic signature. And here's the part that made physicists lose their minds. If WIMPs formed in huge quantities during the Big Bang and then gradually reduced their numbers through self-annihilation, the predicted leftover abundance lands almost exactly on the observed density of dark matter. That coincidence is so clean it got its own name, the WIMP miracle. But detecting something that doesn't interact with light is, not ideal. The strategy is almost comically difficult. You take about 10 tons of ultra-pure liquid xenon, cool it to cryogenic temperatures, and bury it deep underground inside the LX Zeppelin detector. Then you wait. You're hoping a single WIMP will bump into a single xenon atom hard enough to make the nucleus recoil. That recoil emits photons and kicks out electrons, which get drawn upward into xenon gas, releasing more photons. Light detectors at the top and bottom of the tank pinpoint exactly where the collision happened and how much energy it deposited. We're talking tens of kilo-electron volts. Extraordinarily small. The 2024 LZ results represent the most sensitive WIMP search ever conducted. They excluded WIMPs with masses between about 9 and 10,000 gigaelectron volts, setting world-leading limits across that range. Confirmed WIMP events detected? 0. But the detector did successfully identify solar neutrinos through coherent elastic neutrino nucleus scattering, confirming it can pick up nuclear recoils that look exactly like what a WIMP hit would produce. The instrument works, the particle just hasn't shown up, and there's a ceiling approaching. As detectors get more sensitive, they start picking up neutrinos from astrophysical sources that become indistinguishable from WIMP recoils. Scientists call this the neutrino fog. Next generation detectors should either find WIMPs in the remaining parameter space or rule out this entire candidate class. Supersymmetric neutralino models, once the golden child of WIMP theory, have already had massive chunks of their parameter space eliminated. WIMPs might still be the answer. But the window is closing fast, and there's another candidate waiting in the wings that takes a completely different approach: axions. Here's the thing about axions. They weren't invented to explain dark matter. Nobody sat down and said, let me design the perfect dark matter particle. Axions fell out of a completely unrelated problem in quantum chromodynamics called the strong CP problem. Basically, the math governing the strong nuclear force says it should violate charge parity symmetry. It should treat matter and antimatter differently in specific measurable ways, but it doesn't. The strong force respects CP symmetry almost perfectly, and nobody could figure out why. In 1977, Roberto Pecci and Helen Quinn proposed a new symmetry to fix this. When that symmetry breaks, it produces a new particle as a byproduct. That particle is the axion, named by Frank Wilczek after a laundry detergent because it cleaned up the strong CP problem. And it just so happens that this accidental particle has exactly the right properties to be dark matter, which is, convenient. Unlike WIMPs, which are heavy, axions would be absurdly light. We're talking masses in the microelectron volt range for conventional models. Ultralight fuzzy dark matter versions push that down to 10 to the negative 22 electron volts. That's a number so small it barely qualifies as existing. Now here's where the detection method gets genuinely weird. The Axion Dark Matter experiment, ADMX, thought it doesn't smash particles together or wait for something to bump into a xenon atom. It's basically a giant radio tuner. The idea is that axions, when exposed to a powerful magnetic field, should convert into photons through the inverse Primakov effect. So ADMX uses a superconducting magnet applied to carefully tuned resonant cavities, scanning through different frequencies centuries, like someone slowly turning a radio dial, listening for the faintest possible signal of dark matter converting into microwave photons. This thing took over 30 years to reach the sensitivity needed to plausibly detect dark matter axions in the well-motivated DFSZ model range. 30 years of R&D for a radio that listens to nothing, but that nothing might be everything. Recent runs have excluded DFSZ axions across narrow mass windows in the few microelectron volt range, each probing parameter space that had never been touched before. No confirmed detection yet, but the parameter space is shrinking. Fermilab scientist Aran Chu, one of the co-spokespersons for ADMX, has expressed confidence that if dark matter axions exist within the frequency bands they're scanning, detection is a realistic prospect. The radio just has to hit the right station, but if actions are the elegant theoretical solution to dark matter, the next candidate is the brute force approach. Forget exotic particles. What if dark matter is just regular stuff we can't see? Machos. Here's the thing. After everything we've covered, after all the exotic particles and impossible detectors and experiments buried miles underground, the most obvious explanation for dark matter is also the most boring one. Maybe it's just normal stuff that doesn't glow. That's literally what machos are. Massive astrophysical compact halo objects, black holes, neutron stars, brown dwarfs, white dwarfs, faint red dwarfs, same protons, neutrons, and electrons as everything else, just drifting through galactic halos, emitting little or no radiation, invisible not because they're exotic, but because they're dark, like the name suggests. And honestly, this should work. The universe is full of dead stars and failed stars and collapsed stars. Why wouldn't a bunch of them be floating around unseen, adding mass to galactic halos? It's so intuitive, it almost feels like cheating. The way you find them is through gravitational microlensing. A macho drifts in front of a distant background star, its gravity bends the light, and the star temporarily brightens. You can't see the macho itself, but you can see its gravitational fingerprint. Starting in the 1990s, the macho collaboration observed millions of stars in the Large Magellanic Cloud looking for exactly these events. By 2000, they claimed detection of machos that could account for roughly 20% of the galactic dark matter halo. 20%. Not nothing. But then, the EROS-2 collaboration ran the same kind of search with greater sensitivity, and they didn't confirm the findings. Their analysis constrained machos to less than 8% of the halo dark matter. Then, Deep Hubble surveys delivered another blow. Less than 1% of the halo mass is red dwarfs. 1%. And Big Bang nucleosynthesis simply couldn't have produced enough baryonic matter to account for the missing mass while staying consistent with observed light element abundances. Either the math doesn't work. So, machos are effectively ruled out. The simplest, most intuitive answer, that dark matter is just regular matter we can't see, doesn't hold up, and that's the real punchline of this entire video. We know dark matter is real. Galaxy rotation curves, gravitational lensing, the cosmic microwave background, the bullet cluster. The evidence stretches from Zwicky's 1933 observations through Rubin's work in the 1970s all the way to modern experiments today. The question stopped being does dark matter exist a long time ago. Now it's just what is it? And after nearly a century of searching, that answer remains one of the biggest unsolved problems in all of physics. Whatever dark matter is, it's something we haven't found yet, which is, not ideal. If you enjoyed this video and want to see more, click the video on the screen now.